Okay. So the last time we were here, we were talking, oops, hold on, what's going on here? Oh, let me share my screen. Okay, and then let me do this. Okay, why is this? Oh, okay, let me try. Okay. All right, so the last time we were here, we were introduced to gases and the kinetic molecular theory. And the very last thing we discussed was Charles' law. In fact, the two last things that we discussed were Boyle's law and Charles' law. And okay, what's going on here? For some reason this is stuck and I don't know why. Okay. I don't know why this, okay, let me try something here. Let me go to here, and I'm just going to simply pull up another, if possible, another slide or the same slide. Okay, so let me scroll down to, we talked about the different types of instruments for measuring pressure as well. And then we talked about Boyle's law. And just to remind you what Boyle's law says, basically Boyle's law says P1 V1 is equal to P2 V2. And then we discussed that some more, did an example, and then we went to Charles' law, which says that V1 over T1 is equal to V2 over T2, right? And we did an example of that. So that's what we have covered so far. So the next law we're going to talk about is Avogadro's law, which relates the moles of a gas to the volume. And basically what that law says, as you can see here in words, is that at a fixed temperature and pressure, the volume of a gas is directly proportional to the amount of gas in moles, or to the number of molecules of gas, all right? So basically, we can express it mathematically this way. The volume is proportional to N. I don't know how many of you are familiar with the proportional sign, but basically what this means is that whatever change that occurs for one end of this equation or this relationship here, a similar change will take place. In other words, if N is doubled, then V is doubled. If N is tripled, then V is tripled, and so on and so forth. Another way of expressing it is V is equal to Cn, where C is a constant, V is the volume, N is the number of moles, and therefore you can rearrange it to get V over N is equal to a constant, which means that there's another way you can write this, and I'm going to squeeze this. Okay. All right, for some reason my pen function is not, oh, okay, it's working now. So V1 over N1 is equal to V2 over N2, right? So this is another way of mathematically representing the relationship between volume and the number of moles, all right? Now, in this case, what you have to make sure, if you're using this law, is that the temperature and the pressure will be constant, right? So if the temperature and pressure are not constant, then this relationship will not hold, all right? So as you can see in this law and in the other two previous laws, there are two variables that has to be fixed in order for these laws to work, all right? So later on, we're going to see what do we do when all the variables change. But that's for later on, after talking about Avogadro's law here. Now, at this juncture, I want to introduce, or I should say reintroduce, because you should have met this before, the whole concept of standard temperature and pressure, right? And that's particularly important when you're comparing gases in terms of their behavior, right? It makes no sense that you compare gases if you don't hold variables constant, and especially the temperature and pressure. So what the powers decided to do, and I think this is actually IUPAC, International Union of Pure and Applied Chemists, but I could be wrong. They decided to adopt what we call a standard temperature and standard pressure, which would make it meaningful for us to make comparisons between gases. So they decided that the standard temperature would be 0 degrees Celsius or 273 Kelvin, and the standard pressure would be 1 atmosphere, right? Or abbreviated, just called STP. So whenever you see this expression or this abbreviation STP, it means standard temperature and pressure, which means that the temperature is 0 degrees Celsius and the pressure is 1 atmosphere. Also, I want to reintroduce to you the concept of molar volume, right? Which by definition is the volume occupied by 1 mole of a gas, all right? And it turns out that under STP conditions, the molar volume of an ideal gas is equal to 22.4 liters, all right? And we can actually mathematically prove this. In fact, I think I'll do it later on, but we have to cover some other topics first before we get to this. But for now, you can just accept that under STP conditions, under the conditions where the temperature is 0 degrees Celsius and the pressure is 1 atmosphere, under those conditions, the volume of 1 mole of an ideal gas is 22.4 liters, all right? Okay, so that's as far as Avogadro's law is concerned. So based on what we have just learned, let's look at this example here. Let me see if my pen is working. Okay, it's working. Okay, so this question says, calculate the volume occupied by 4.1 kilogram of methane, and it gives you the formula of methane gas at STP, all right? So basically, you're given 4.11 kilogram of methane, and you're asked to determine the volume in liters of that gas at STP, all right? So the first thing I would do is start off with 4.11 kilograms of the methane gas, and I will convert it to grams. So of course we know that 1 kilogram is equal to 1,000 grams. So I would put 1,000 grams of methane above and 1 kilogram of the same below, so that this will cancel out with this. And then the next conversion factor is where I would convert from grams of methane to moles of methane. And if I remember correctly, the molar mass of is 16 point something. Let me do my calculator thing. Where is it? I had it here. Okay. Let me do it here. My molar mass calculator that I like to use. So I'm going to type in my formula, CH4, and 16.04. Okay, so the molar mass of methane is 16.04. So the way I would represent it here, go back to this. So the way I'd represent it here is that I'm going to put 16.04 grams of methane down here as a denominator and 1 mole of methane above as the numerator. So this unit will cancel out with this unit. And then we get to the next conversion factor where we would go from moles of methane to liters of methane, which is what the question is asking for. But remember, the question says that the conditions are STP conditions. And as I said before, under STP conditions, 1 mole of any gas, and it doesn't matter what the gas is, including methane, will occupy a volume of 22.4 liters. So the way I would represent it in this conversion factor is that I'm going to put 1 mole of methane down here, and up here I'm going to put 22.4 liters of methane above, so that this unit will cancel out with this unit. And then we do our number crunching, which I'm going to do here. 4.11 times 1,000 divided by 16.04 times 22.4. And according to my calculations, when rounded off to 3 sig figs, the answer becomes 5.74 times 10 to the 3 liters of methane. And that is, or should be, the final answer. All right? Any questions about this example? Any questions? Okay, So, moving along. So we have learned about 3 gas laws so far. In fact, let me get out of this here and just show you something. I'm going to write something on my tablet here. Okay, so far we learned about 3 gas laws. Boyle's law, which is PV is equal to a constant. And then we have Charles' law, which is V over T is equal to a constant. And then Avogadro's law, which is V over N equals to a constant. As I said before, there are a couple of things that need to be held constant in each case. So for example, in the case of Boyle's law, the number of moles and the temperature must be constant in order for this law to hold true. In the case of Charles' law, the number of moles and the pressure must be constant, all right? And then in the case of Avogadro's law, the volume, I'm sorry, not the volume, the pressure and the temperature, must be constant. So in each of these cases, these variables would have to be held constant. So this begs the question, what would be the case if all 4 variables are held constant? If the pressure, the number of moles, the temperature, and the volume, if they're all held, if they all vary, I should say, not held constant, but if they all vary. Well, that brings us to a new law, which is not really a new, it's a combination of these 3 laws, known as the combined gas law. And basically what that law says is that PV over NT is equal to a constant, all right? So basically, if you have the 4 variables here changing, then basically when you put them in this equation, you should get a constant here, right? Another way of stating this would be P1 V1 over N1 T1 equals to P2 V2 over N2 T2, all right? So this is another way of expressing the combined gas law, all right? So that's a combined gas law, which is used when all 4 variables change. But if 2 of the variables are changed or held constant, then basically this equation will be reduced to any one of these laws. For example, remember we said up here that for the Boyle's law, the number of moles and the temperature is constant, I'm sorry. So that means that N1 T1 is going to be equal to N2 T2. So if you cancel these 2, you're going to end up with P1 V1 equal to P2 V2, which is of course Boyle's law, right? And you can do a similar exercise with keeping the number of moles and pressure constant and keeping the pressure and temperature constant, all right? Okay, so with that said, let me go back to this. So this is basically saying the same thing, but I prefer to show you the way I just did, but the end result is the same thing. P1 N1, P1 V1 over N1 T1 is equal to P2 V2 over N2 T2, all right? So that's the combined gas law. Okay, so based on what we have just talked about here, we should be able to do this question. So this question says the flasks pictured in figure 1.11 contain oxygen. So that's one important information given here. Oxygen, I don't know if it become important in terms of actually solving the problem. The one on the left is at STP, we know what that means. And the one on the right is at 100 degrees Celsius. What is the pressure at 100 degrees Celsius, right? So the equation that comes to mind would be P1 V1 over N1 T1 is equal to P2 V2 over N2 T2, all right? Now, in this case, there are 2 things that will be held constant. One of them would be the volume. Why? Because basically the volume of the 2 flasks here would be the same, all right? So therefore, the V1s will cancel out with the V2 here. And then the other thing that will cancel out is the amount of gas, right? The amount of gas would be the same, so N1 and N2 will cancel out here. So this will be reduced to P1 over T1 is equal to P2 over T2. And by the way, this is also another gas law. The name of this gas law is, if I remember correctly, Gay-Lussac's law. Gay Lusak's, I don't know if I'm spelling this right, law. All right, so this is a fourth gas law which govern the behavior of gases. All right. Okay, so now we have to determine what the question is asking for. And the question is asking for the pressure at the elevated temperature. So therefore, I would basically rearrange this to solve for P2. And the way we would do this, of course, in your algebra course, you should learn this. You multiply both sides by T2. And you're going to get P2 is equal to P1 T2 divided by T1. Let me see if I can fit those numbers in. So P1 is going to be the initial pressure, which is, let me see. They didn't ask for the units, so I'm going to assume 1.00 atmosphere times T2. Now T2 would be the higher temperature, which is 100 degrees, but of course, remember we said that when using these laws, the temperatures must be expressed in Kelvin. So I'm going to put 373 Kelvin here. And then all of that would be divided by T1, which is standard temperature, which is 0 degrees Celsius, which is the same thing as 273 Kelvin. And then we do our number crunching. So it's going to be 1 times 373 divided by 273. And according to my calculation, when rounded off to 3 sig figs, the answer becomes 1.36, and the units would be atmospheres because the Kelvin units will cancel out here and here. All right. So that's basically how that is done. All right. Okay. Any questions about this one? Any questions about this example? Okay, moving along. Oh, there's a question here. So let me erase this to see what the question is asking. Let me erase this here. So the question says, what pressure would be exerted if the vessel was transferred to an oil bath at 200 degrees? Okay, so basically what that means is that T2 would be equal to 200 degrees, which means that, okay, let me do it up here. So basically we're going to use the same equation here, and the only difference is that we're going to put 200 degrees, or actually in Kelvin, so 200 plus 373 would give you 573 Kelvin. So therefore, P2 in this case would be equal to P1, which is 1.00 atmospheres, times 573 Kelvin, divided by 273 Kelvin, and that would be equal to 573 divided by 273. So according to my calculation, when rounded off to 3 sig figs, that would give you 2.10. And the units again would be atmospheres. All right. So basically one can see that as the temperature increases, the pressure of the gas increases, which is basically what Gay-Lussac's law is saying. All right. Which makes sense if you think about the kinetic molecular theory, because according to the theory, since the gas have particles that are moving quickly, if you impart more energy to the gas particles, the particles will move at a faster speed, and therefore they will hit the walls of the container with greater force and frequency, and therefore the pressure of the gas exerted against the walls of the container would increase. So that's basically how the kinetic molecular theory is used to explain this observation that as the pressure increases, as the temperature increases, the pressure increases. All right. Okay, any questions about this? Any questions? Any questions? Okay, so let's talk about the ideal gas law. So the ideal gas law is basically an offshoot from the combined gas law that we talked about. Now remember we said, according to the combined gas law, PV over NT is equal to constant. Well, it turns out that the constant of this equation has a value, and this is the value right here. It's equal to 0.08206, and there's some more digits after that. And please note the units. The units would be liters atmospheres divided by mole Kelvin. Very important, all right? Now for our purposes, we will just round this off to 0.0821 liters atmospheres over mole Kelvin, right? For all purposes, that's what we're going to use. We're going to run it off the 3 sig figs, all right? So basically, this is the ideal gas law here. In most textbooks, you'll see it more likely expressed as this. It's the same thing. PV is equal to nRT. And basically, this equation can be used to find basically any one of these different variables if you know the other four. Of course, the R here is always going to be a constant. That doesn't change, all right? But if you, for example, know what the pressure, volume, and the number of moles are, then you can calculate the temperature, all right? Okay, so in terms of the units, right? Remember I said that the units is this. Now, that would be true if the pressure is in atmospheres, the volume in liters, of course, N would be, would have the mole unit, and the temperature would be in Kelvin, right? So if these are the units associated with these different variables, then this would be the actual value of R, all right? Now, you can have R expressed in other units, and that would change the numerical value of R. So for example, if P is in atmospheres, right? And if the temperature is in Kelvin and mole, of course, would be mole, and the volume in liters, then, of course, as we said before, R is equal to this. However, if you switch from P being expressed in atmospheres to P be expressed in pores, then this would be the value of R, the molar gas constant. And then here, if the pressure is expressed in pascals and the volume is expressed in meters cubed, then the value of R will be this right here. And the units will be joules per mole Kelvin, all right? Now, let me just say this. I don't anticipate you using this value here in any problem solving, but you can if you want to. But I don't think it's absolutely necessary for you to know or use this value here. In the vast majority of cases, you'll be using this value here, all right? But there's one particular instance we're going to see later on where we need to use this value here along with its unit, all right? So that's for later on when we're looking at diffusion of gases. There's one equation where the R value is used, but you have to use this value here in order for that equation to be useful, all right? So this is something for you to keep in mind later on. But in the most cases where you're dealing with gases, you'll be using this value right here. And as I said before, we'll be rounding this off to 3 sig figs in future problem solving exercises. Okay, so let's look at this example here. So this question says, what is the pressure? So the question is asking for the pressure that is exerted by 0.508 moles of oxygen in a 15.0 liter container at 303 Kelvin, all right? So it gives you the pressure, it gives you the moles, it gives you the volume, it gives you the temperature. So the first thing that would come to mind is the PV is equal to nRT equation. That's the first thing that would come to mind, all right? So since the question is asking for the pressure and it gives you everything else, it gives you the volume, number of moles, the temperature, and we know what R is, I would solve for P. So P would be equal to nRT over V. And then I would put the numbers in. So N is equal to 0.508 moles times R, which remember is 0.0821 liters atmospheres over mole Kelvin, multiplied by the temperature, which is 303 Kelvin, and then divided by V, which is the volume, which is 15.0 liters, and that's the setup, all right? And this is what I'm about to show you is the reason why I'm a stickler for including the units as a part of the whole process, right? Whenever you're solving any problem mathematically where units are involved, make sure that the units are actually involved and shown in the setup. So in this case here, this is how the units will cancel out, and you end up with one final unit in your answer, right? The mole units will cancel out here and here. The Kelvin units will cancel out here and here. The liters units will cancel out here and here. So the only unit remaining would be the atmosphere unit. So let me write atmosphere here. And then you simply do the calculation. So 0.508 times 0.0821 times 303. And then you divide by 15. And that gives you, according to my calculation, 0.842 atmospheres. And that would be the final answer. All right. Okay. Any questions about this example? Any questions? Okay. So moving along, here's another example. Now, this one is very similar to what we did before, but it's a bit more complicated. One difference is that this question is asking for the volume, and the other difference is that it doesn't give us the mass, it gives us the mole of the, I'm sorry, it doesn't give us the moles, it gives us the mass of the gas, it gives us the formula of the gas, it gives us the pressure in torr, and it gives you the temperature in degrees Celsius, right? So the question is asking for the volume. So therefore, what I would do is rearrange the ideal gas equation. Give me 1 minute. Let me just turn on this fan here. Hold on 1 minute. Okay, sorry about that. Excuse me. So I would write down a rearrangement of the ideal gas equation, which is V is equal to nRT over P. And then now I would try to find each of these terms, right? So the first one is N, which is the number of moles. We're not given the moles, but we're given a mass. But we know how to convert from mass to moles. So we're going to start off with 16.0 grams of methane. And then we have to convert to moles. So it will be 1 mole of methane. And the molar mass, I think we did this before. If I remember correctly, it's 16.04 grams, right? Somebody can correct me if I'm wrong, but I think that's the molar mass of methane, all right? And then we multiply by R. What am I doing? Let me erase this here. Okay, so we multiply by, okay, you know what? Let me keep this here. R, which is 0.0821 liters atmosphere over mole Kelvin. And then we multiply by the temperature. Now the temperature here is 18 degrees Celsius. If you add 18 to 273, that would give you the corresponding value in Kelvin. So this is 291 Kelvin. So I'm going to put 291 Kelvin here. And then I will divide by the pressure. Now in this case, they gave us the pressure in torr, 720 torr. And if you remember, we said that 760 torr is equal to 1 atmosphere. So the way we would represent this here, we're just going to put 1 atmosphere here and 760 torr down here. Okay, so again, you see the setup. Again, you see that I've included the units as a part of the setup because I need to show how the units will cancel out. So the grams will cancel out with the grams here. The moles will cancel out with the moles here. The Kelvin will cancel out with the Kelvin. The torrs will cancel out here and here. And the atmospheres will cancel out here and here. So your final answer will be in liters. So let me do this calculation here. 16 divided by 16.04 times 0.0821 times 291, whoops, 291, divided by, and then let me put that in parentheses, 720 divided by 760. Okay, so according to my answer, and folks, while I'm doing these problems, please work it along with me because I could be wrong. I'm willing to stand corrected. So just check behind what I'm doing just to keep me on track. Okay, so according to my calculations here, rounded off to 3 sig figs, this is going to be equal to 25.2 liters. All right. So that's basically how that is done. All right. Any questions about this one? Any questions? Any questions? All right. So Okay, now what we're going to do is look at how we can determine some other important information concerning gases based on the ideal gas law. And the first one that we're going to look at is how we determine the molecular mass of an ideal gas. All right. And first thing I'm going to state here is the relationship between the mass in grams and the molar mass. And we all know what this relationship is. So what I'm going to do here is use uppercase M to represent the molar mass, which of course is the mass per mole of a substance, and M represents the mass in grams, right? So if we're going to use these two symbols to represent these two different terms, then the relationship between them is given by this equation. The molar mass is equal to the mass in grams divided by the number of moles, which can be rearranged algebraically to give you this relationship. The number of moles is equal to the mass in grams divided by the molar mass, all right? So this is something that we have to keep in mind here. Now, the other relationship we're going to look at is what we saw earlier in this chapter, the ideal gas equation, which can itself be rearranged to solve for N. N, in this case, would be equal to PV over RT. So N is equal to M over M, N is equal to PV over RT. So we can equate these two to each other, and this results in this relationship here. Lowercase m divided by uppercase M is equal to PV divided by RT. And therefore, we can rearrange this equation to solve for uppercase M, which is the molar mass, right? The molar mass is equal to lowercase m times RT over PV, and that would be the equation you'd use to determine the molar mass. And remember, the molar mass of a gas will be the same thing as the molecular mass in terms of the numerical value, all right? The difference is, and this is something that we covered in chapter, I think it was 3, the difference is that the molar mass will be expressed in grams per mole and the molecular mass will be expressed in AMU, but numerically they're the same. So if you were to use this equation to find the molar mass, then basically you just express the same number as the molecular mass, excepting that you're going to use AMU, all right? And there's an experiment that I used to do, and well, up until the pandemic, of course, with my class, with my lab classes, my Chem 1 lab classes, where we actually use this idea here, and it works very well. Again, this is one of those situations where I wish we could actually have the hands-on experience of doing this experiment, but unfortunately, that will not be the case for this semester. Unfortunately, we have to basically do everything online as a result. Okay. So that's one equation that is derived directly from the ideal gas equation, which is used to determine the molar mass / the molecular mass of a gas, all right? So based on that equation, we can determine the molecular mass of this gas given in this question. So they gave us the mass in grams, they gave us the volume, they gave us the pressure in atmospheres, and they gave us the temperature in Kelvin. And the question is asking for the molecular mass of the gas, all right? So what I would do is find the molar mass of the gas and solve for that using this equation here, all right? And then basically express that same number in an AMU value or AMU units, right? So let's plug in the different values into this equation. So M is the mass of the gas. And let me just say here, I just remembered something. Students very often confuse the molar mass and the mass of the gas, right? Very often students confuse those two, all right? Especially when they're reading the question and they're trying to interpret what is what, all right? So it's very important that when you're getting a question like this, that you know what the molar mass is and what the mass of the gas is, and you put them in their appropriate places in the equation, all right? So that's just something that I've noticed, you know, over the years when I'm grading exams and so on. Okay, so back to this problem. So the mass of the gas is 0.550 grams times R, which doesn't change, 0.0821 liters atmospheres over mole Kelvin, times the temperature, which is 289 Kelvin, all divided by the pressure, which is 0.0 0.968 atmospheres times the volume. What's the volume? Oh, 0.200 liters. All right. So that's a setup. And here is how the units will cancel out. The atmospheres will cancel out with the atmospheres here. The Kelvin will cancel out with the Kelvin. The liters will cancel out with this liters. So the only units remaining would be grams divided by moles, which would be, of course, the units of molar mass, grams per mole. So we're going to do our calculations here. 0.550 times 0.0821 times 289 equal divided by 0.968 equal divided by 0.2. So according to my calculations, and somebody can correct me if I'm wrong, according to my calculations, when rounded out to 3 sig figs, this becomes 67.4 grams per mole. All right. Now remember, that's the molar mass. All right. That's a molar mass. But the question is asking for the molecular mass. Molecular mass. Which is going to be equal to the same thing numerically, 67.4, but the units would be AMU. So this is what the question is asking for. It's asking for the molecular mass. All right. Okay. Any questions about this one? Any questions? No questions? Whoops. Okay. So let's look at this question. And this time, I'm going to turn it over to you guys. All right. So this question gives you some information about a liquid that is vaporized. So basically it becomes a gas. It gives you the temperature. Let me underline it here. 100 degrees Celsius. Gives you the pressure, 755 torr. It gives you the volume, right? 185 mils. And it gives you the mass, which is 0.523 grams. Okay, so based on what we have done in the previous example, what would be your very first step in solving this problem? Excuse me. Anybody? Let me start you off. This is the equation you're working with. All right? So what will be the first step? Okay, what is M? Let's start off with that. Come on, guys. It's obvious. What is M? Can somebody tell me? Okay, I see two persons here. Jacob? Cameron?
Is it the grams?
Yeah, the value in grams, right? Which is what?
It should be 0.523.
Yep, 0.523 grams multiplied by R. What is R?
R. Is that going to be the milliliters? Or is
No,
that going to
R is the
Okay.
molar gas constant. Remember what that is?
No, not off the top of my head.
0.0821 liters
Okay.
atmospheres over a mole Kelvin, right? That
Okay.
doesn't change. All right.
Okay.
What's the temperature?
Temperature is 100 degrees Celsius.
But what do we need to do to that?
You need to transfer that to Kelvin, yeah?
So that becomes what?
Let me see.
What do you add to 100 to convert it to Kelvin?
Let's see. Is it 373.15? Or
No,
is that
273.
273?
Yeah. So
Okay.
this becomes, I guess I misunderstood your response.
Yeah, so it'd be 373.
Right, the answer is 373. Thank you. I'm sorry.
Yeah.
I thought you were talking about what you add to it. What you add to it is 273, right?
Yeah.
Okay,
Yeah.
so that goes here. All right. Then we
Okay.
divide by the pressure. So what's the pressure in this case?
Would it be the 755?
755 torr. Okay. But we need to convert this to atmospheres because we have the atmosphere unit here, right? So how do
Yeah.
we convert that to atmosphere?
Um,
I think we did something like that in a previous example. What do we put here and what do we put down below here?
so you have to get to atmosphere. Is this where we did in the last problem where it was like the 760?
Exactly. 760 torr
Okay.
here. And up here we have what?
Would it be the 1 atmosphere?
1 atmosphere, correct. Okay. And then finally we multiply by the volume. Now they gave us the volume as
185 milliliters.
85 mils, but we need to convert this to liters, right?
Yeah.
So that means we put what up here?
So that would be 1 liter, correct?
1 liter divided by?
It'd be that over. Is it 1,000?
1,000, exactly. 1,000 milliliters. Okay, very good. So that's the setup, right? And again, the units are important. The torrs will cancel out here and here. Milliliters will cancel out here. Liters will cancel out here and here. Oh, by the way, this should be Kelvin. I forgot to put that unit here. That will cancel out with the Kelvin here. And the atmospheres will cancel out here and here. And we are left with the final units being grams per mole, right?
Yeah.
So we have to do our calculations. 0.523 times 0.0821 times 373 divided by 755 divided by 760. And then we divide by 0.185. According to my calculations, I got 87.1 grams per mil, which means that the molecular mass, which is what the question is asking for, is equal to 87.1 AMU. And that's how that one is done. All right. Okay. Any questions about this? Any questions?
No.
Okay. All right. Now another important information about a gas we can determine based on the molar gas law or the ideal gas law is a formula for determining the gas density. And in fact, we can derive the equation for this from the equation that we were just using for the molar mass, right? So basically, the first thing I want to mention here, is that gases are much less dense than liquids and solids. I think I made that point before at the very start of this particular chapter. And therefore, as a result, their densities are usually reported in grams per liter, all right? Whereas in the case of solids and liquids, we tend to express their densities in grams per cm cube or grams per mil. So what we're going to do is look at this equation, which we were looking at just now. And if you rearrange this equation to solve for m over v, which is, of course, the definition of density, you're going to get m over v is equal to mp over rt, right? So therefore, m over v is the density. So basically, we can replace that with d, the density, and that will be equal to mp over rt, all right? And therefore, we can use this equation here to calculate the density. If we know what the molar mass is, if we know what the pressure is, and if we know what the temperature is, then we can easily calculate the density using this equation. Before we look at some examples using this equation, I want to point out one important point, and that is that we can see that there's some relationship between densities and the other variables on the other side of the equation. So for example, the density is directly proportional to the molar mass, right? So what that means is that if you have two gases and everything else is the same, the pressure and the temperature is the same, then the one with the greater molar mass would be the one that will be more dense, all right? If we look at the relationship between the density and the pressure, you'll see that as the pressure increases, the density increases if everything else remains the same. And in the case of temperature, there's an inverse relationship between the density and the temperature, in that as the temperature increases, the density will decrease, right? So we see that there's some relationship between the density and the molar mass, pressure, and temperature individually, all right? Okay, so with that out of the way, let's look at this particular example. It says calculate the density of methane gas, and it gives you the formula of methane in grams per liter at 25 degrees Celsius and 0.978 atmospheres. So the density formula is what we just saw earlier. MP over RT. So all we have to do is plug the numbers in. Now, again, the molar mass of methane, if I remember correctly, is 16.04 grams per mole times the pressure, which is 0.978 atmospheres, divided by R, which is 0.0821 liters atmospheres over mole Kelvin, times the temperature, which is 25 degrees, which we have to convert to Kelvin, which will give you 298 Kelvin, because you add 273 to that. So that will give you 298 Kelvin here. And then we do our usual cancellation of units. The moles will cancel, the Kelvin will cancel, the atmosphere will cancel. So you're left with your answer expressed in grams per liter. So let me do the calculations here. It's going to be 16.04 times 0.978 divided by 0.0821 equals divided by 298. And according to my calculations, the answer is 0.641 grams per liters, all right? So that's basically how this is done, all right? Any questions about this one? Any questions? Any questions? Okay, so let's look at this one. Now this one is using the same equation, but the difference is this question is asking for the pressure, right? Also, the question does not give you the molar mass, but it gives you the formula for the gas. It gives you the temperature in Celsius, and it gives you the density, right? So the equation we're using is the same one, which is the density, density is equal to MP over RT. What the question is asking for is the pressure, right? So if we rearrange this, we're going to get the pressure is equal to D RT over M, the molar mass. And then again, we just plug the numbers in. So this becomes 1.50 grams per liter times R, which is 0.0821 liters atmospheres over mole Kelvin times the temperature, which is 25 degrees Celsius, which when you add 273, this becomes 298 Kelvin, 298 Kelvin. And then we divide all of that by the molar mass. Now the molar mass of oxygen, if you look it up in the periodic table and multiply by 2, would be 32.00 grams per mole. So that will go down here, 32.00 grams per mole. And again, we're going to look at some units canceling out. The grams will cancel out here and here. The moles will cancel out here and here. Kelvin will go here and here. And the volume in liters will go here and here. So what we're left with will be 1.50 times 0.0821 times 298 equal divided by 32. And according to my calculations, the final answer here would be 1.15. And the units, of course, would be atmospheres. All right. And that's basically how this would be solved. All right. Any questions about this one? Any questions? Any questions? Okay. So I just thought it was important that we go through some examples. These are typical of the type of problems that you will be facing in your future assignments, tests, etc. All right. And as I always say, the more problems you do, the better you become at it, the more efficient you become at it, and you're more likely to do well in your future assignments and tests. Okay, so the next law we're going to talk about is the law of combining volumes. And this deals with gaseous reactions, right? Reactions where all the different components or all the reactants and products are gases. So what this law says is that when gases measured at the same temperature and pressure are allowed to react, the volumes of the gaseous reactants and products are in small whole number ratios, all right? And to explain that particular law using an example, if you look at the reaction of, let's say, hydrogen and oxygen to form water, right? What you'll find is that the volume ratios, provided that the temperature and pressure are the same for all the gases, the volume ratios between the hydrogen and the oxygen would be a 2-to-1 ratio, right? And that comes directly from the stoichiometry of the balance equation, right? So let me get out of this here, my writing tablet to explain this further. So let me remove this. Okay, so let's say, well, the equation for the reaction is H2 gas plus O2 gas to give H2O gas, and to balance this, we're going to need a 2 here, right? Now we already know from our understanding of stoichiometry what this equation is telling you in terms of the relative amounts of the different substances involved. So one way of reading this, we can say that 2 moles of hydrogen will react with 1 mole of oxygen to form 2 moles of water, right? So that's one way of interpreting this equation. Now, the thing is that if the temperature and pressure are constant, so let me just write down here, if T and P are constant, right, then we can interpret this equation as 2 volume ratios, or 2 volume units, I should say, of hydrogen will react with 1 volume unit of oxygen to form 2 volume units of water. And it doesn't matter what the volume units are. The volume units could be any unit of volume, centimeters cubed, liters, gallons, quarts, it doesn't matter, right? What you'll find is that the volume ratios will be the same as the mole ratios if the temperature and the pressure are constant or the same for all the gases, all right? So that's basically what this law is saying. Here's another example. Let's say we have, let me draw a line here. Let's say we have a reaction between nitrogen and hydrogen, right? To form NH3. Of course, to balance this, and these are all gases, by the way. These are all gases, all right? So let's say, well, we have to balance this first. So 2 here, 3 here, right? What you'll find is that, again, the same idea or concept will apply here, in that 3 volume ratios of nitrogen will react with 1 volume unit of hydrogen to form 2 volume unit of ammonia, right? And again, it doesn't matter what the volume units are. Again, it could be liters, gallons, whatever. The volume units or the ratios of the volume would be the same as the mole ratios. Again, if the temperature and the pressure of all the gases are the same, all right? So that's basically what this particular law of combining volume is all about, all right? So as stated here, let me go back to my full screen. As stated here in this very last sentence, we don't need to know what the actual conditions are, right? So in other words, we don't need to know what the temperatures and pressures of all the gases are, accepting that they're the same, right? The temperature and pressure of all the gases must be the same, excuse me, in order for this particular law to work, all right? Okay, so this is just an illustration of what we were just talking about, right? So what these different flasks represent, I think this is the reaction between hydrogen and oxygen to form water, right? So basically, each flask has the same volume. So we have 2 volume units of hydrogen reacting with 1 volume unit of oxygen to form 2 volume units of water, all right? So the volume ratios is the same as the mole ratios, as I was saying before. So this is just re-emphasizing what I just said. And let me also reemphasize that the temperature and the pressure must be fixed. If the temperature and pressure are not fixed, then this will not hold true, all right? Okay, any questions about this? Any questions? Okay, so here's an example based on what we have just covered here. Question says, how many liters of O2 are consumed for every 10.0 liters of carbon dioxide produced in the combustion of liquid pentane, and this is liquid pentane, if all the volumes are measured at STP, all right? So basically it's C5H12 that is reacting with, now it says here, combustion, right? So what is the C5H12 reacting with? Anybody? Based on the information provided. C5H12 will be reacting with what? Anybody? What is a combustion reaction? Anybody? We did this, I think, in chapter 2 or chapter 3. No, I think it's chapter 2, yeah. When you're burning something in air, what are you reacting it with? What component of air will it react with? Hint, hint, hint. Everybody see that? That's oxygen. It will react with oxygen, right? And as the question says, it produces carbon dioxide. But there's another product it will produce. Can anybody tell me what that product is? When a hydrocarbon, which in this case is a liquid, reacts with oxygen, it produces carbon dioxide and what? Anybody? Come on, we all know this. Well, Jacob or Cameron, which of you would like to tackle this one? It's a simple answer. Anybody? Come on. Okay, I give up. It's going to be H2O liquid. I'm sorry, H2O gas, I think. Well, they didn't say what state, so I'm just going to assume liquid. All right. Okay, the next thing we need to do is balance this equation. So how do we go about balancing this equation? And I'm sure you should be able to do this now. How do we balance this equation? It's C5H12 plus O2 to give you CO2 and water. Are you guys awake? Hello? Okay, I need to know if you guys are here. If you're not here, it doesn't make any sense we continue. I need to know if you guys are paying attention. Okay.
It would be, when you put, to balance it all out, you put an 8 in front of the O2, a 5 in the CO2, and a 6 in the H2O.
Okay, so let me see here. You said an 8. Whoops, hold on. You said an 8 here.
And then a 5 in front of CO2.
Okay.
And then a 6 in front of H2O.
Okay, that's correct. Okay, very good. Very good. All right. So that's the first thing we need to do to solve this problem, right? We need the balance equation. You could not do anything else beyond that if you don't get this equation balanced. All right. So the next step is we need to establish the relationship between the carbon dioxide and the oxygen, right? Between these two items.
Okay.
Right? And based on the balanced equation, there's a 8:5 mole ratio, or we can also say that's an 8:5 volume ratio because they're all measured at the same conditions of temperature and pressure, STP, right? So we're going to start off with the 10.0 liters of CO2, and we're going to multiply by the volume ratio, which would be 5 liters of CO2, and up here, 8 liters of O2. So this will cancel out with that. And so that's 80 divided by 5, which gives you 16.0 liters of oxygen. So this is a relatively simple example of the use of the law of combining volumes. All right. Okay, any questions about this one? Any questions? Any questions? Okay. Should I start this one? Okay, let me start this topic here. This will be a bit involved, so I'm just going to start and stop at a certain point, and then we'll continue for next class. All right? Okay, so based on what we have learned so far, we have learned about some laws, Boyle's law, Charles' law, combining volume law, ideal gas equation, and so on. We can combine that kind of information with what we learned in chapter 4 or 3 with respect to stoichiometry, right? Because of course, gases are involved in reactions, and therefore, the stoichiometric principles that will apply also to such reactions like any other reactions. And therefore, some problem-solving exercises will involve utilizing those stoichiometric principles, right? So as stated here, we can use the law of combining volumes for stoichiometry only for gases and only if the gases are at the same temperature and pressure. That is something that we stressed earlier. Now, things are a bit different when the temperature and pressure are changed, right? If the temperature and pressure are different, then basically we have to employ some of the stoichiometric methods that we used in combination with certain gas laws, in particular the ideal gas equation. So basically, if you remember when we were doing stoichiometric calculations, it comes down to having a balanced equation for one, as we saw in the previous example that we looked at. where we establish the mole ratio between two different substances that are involved in the calculation, right? And of course, in order for us to establish that relationship, we need the mole ratio based on the balanced equation, right? So that principle will come in play in the type of problems we'll be looking at when it comes to gas stoichiometry. But the other thing we need to determine in some cases, if we're dealing with gases, is that we need to find the moles of a gas based on other information provided, such as the pressure, volume, and temperature. And of course, that information can be used in the ideal gas equation to find the moles of one substance. And then after using the mole ratio to find the moles of the other substance, then based on what the question is asking for, we can use the ideal gas equation to find either the pressure, the volume, or the temperature, right? So most of the stoichiometric gas problems that we'll be looking at after this would involve that kind of combination of the mole ratio along with the ideal gas equation being used, all right? And here's one such example, and I think this is going to be the last example for today. So this is talking about this equation right here, the reaction between, or the reaction of sodium nitride to form sodium in a liquid state and nitrogen, right? And the question is asking, what volume of nitrogen measured at 25 degrees and 0.980 atmospheres is produced by the decomposition of 62.5 grams of sodium nitride, all right? And fortunately for us, they gave us a balanced equation, all right? Okay, so the first thing I would do is I would start off with the 6.25 grams of sodium nitride, and then I would convert that to moles. So 1 mole of NaN3 divided by the molar mass. So again, I'm going to get out of this and go to the molar mass calculator. And according to this, the molar mass of sodium nitride is 65.01. So I'm going to put, whoops, go back to here, full screen. 65.01 grams of sodium nitride. That will go here, right? Oh, by the way, so that's the moles of sodium nitride. Now, the next thing I'm going to do is look at the mole ratio between the sodium nitride and the sodium, and the nitrogen, I'm sorry. And you see that's a 3:2 mole ratio. So I would represent this as 3 moles of nitrogen divided by 2 moles of sodium nitride. So this, let me cancel the units here. So this would give us the mole of nitrogen. So let me do the calculation here. It's going to be 6.25 divided by, what was that, 60, oh gosh, I can't even read my own handwriting. 65.01. 65.01 times 3 divided by 2. And according to my calculations, this works out to be, when rounded up to 3 sig figs, 0.144 moles of nitrogen. So this gives us the moles of nitrogen, but the question is not asking for the moles. The question is asking for the volume. So how do we get the volume? We use the ideal gas equation. And if you rearrange it to get the volume, that would be equal to nRT divided by P. So we put the numbers in. The N here would be the number of moles here, which is 0.144 moles, times R, which is 0.0821 liters atmospheres over mole Kelvin, times the temperature, which is 25 degrees Celsius, which is the same thing as 298 Kelvin, all divided by the pressure, which is equal to 0.980 atmospheres. And we do our number crunch. Well, let's do the unit cancellations first. So the moles will cancel out here and here. Kelvin goes there and there. Atmosphere goes there and there. So your final answer will be expressed in liters. So 0.144 times 0.0821 times 298 equal divided by 0.980 So according to my calculations, this works out to be equal to 3.59 liters. And that's basically how that is done. So this is a typical gas stoichiometry problem. As you can see, it utilizes the whole concept of stoichiometry. That was the first part, where you given the mass of one reactant and you find out the mass of one product. And then the next step is where you use the number of moles of the product from the previous part to find the volume using the ideal gas equation. All right? Okay, any questions about this example? Any questions? Any questions? Okay, I think that's going to be it for today. All right. But before you leave, let me just let you know that, well, two things. One, remember the presentation tomorrow. You're all invited to attend. I think I've posted the information, the Zoom link online. What's his name? Dr. Bruce Ford will be talking about his career as a meteorologist. If you're interested in science careers or that particular field, you probably want to join that particular discussion. All right. So, you know, please attend that that worthwhile presentation. The next thing I want to say also is that you may have noticed that I've posted the test scores in Canvas. I plan to, I don't know if I'll be able to do it today, but I plan to send you back the graded work. So if you have any questions, you can feel free to, you know, if you think you deserve more points for a particular question, whatever, feel free to contact me concerning that. I'll be available for office hours today from 1 to, wait, today's what? Today's Thursday, from 11 to 5, all right? So I'm hoping to get down to my, to the campus today to do that. If not, more than likely tomorrow would be the day it will be available. So I'll let you know as soon as I've posted. Well, as soon as I send you your graded test, and also I'm going to post the answer key as well. So make sure that you look at the answer key before you call me so that you can see what the actual answers are. I'm still in the middle of grading quiz number, what is it, quiz number 2. In fact, I should be finished with that as well today. So hopefully I'll be able to send you that back as well, your graded work, as well as post the answer keys for that, all right? Okay, I think that's basically all that I have, unless there are any questions you guys. But I think that's basically all I have by way of announcements. So if there are no questions, that's it. Enjoy the rest of your day and your weekend, and I'll see you guys back on Tuesday. All right?